We got to read out, understand the question clearly. Otherwise, you may get a wrong order. So what this question is asking, rank the molecule by the chemical shift, but more D-shielded gets number one, least D-shielded gets five, right? So we're not telling you which proton you need to look at. The probability of, this has to be the one proton, the most D-shielded one. The first task is you're going to find out which proton is most D-shielded, most in downfield. On this one, is this proton going to be most D-shielded? And that's kind of the question. What is the most D-shielded question is this one. That one next to oxygen. That's the probably the most downfield proton. And in this molecule, you can choose this one, you can choose that one, doesn't matter, but that's the one. Same thing for this one. But in this molecule, doesn't really matter, there's no electron withdrawing groups. And this one, you got the bromine here. So this proton is probably the most D-shielded one. So first task is find out which hydrogen is the most D-shielded. And then you kind of have to estimate what will be the chemical shift. But I can clearly say that this one will be the most off-field proton because there's no electron withdrawing groups. That has to be the lowest chemical shift. So I can really figure out that must be, I think the wrong one, that should be 5, right? The least downfield shift, most off-field is 5. So sorry, that should be 5. I made a mistake. So this kind of mistake you don't want to do. You got to put the number for everything. Yeah, embarrassing here, but anyway. Then we're gonna expect the chemical shift. That one, this proton next to carbonyls are typically around 2.1. That's the number we will keep talking about. The alpha hydrogen, alpha means the next to the carbonyl, is actually 2.1, 2.2. It can move around, but this is the only electron withdrawing group, so 2.1 is my guess. And then the next one, if it's an oxygen, it'll pull out more. Other halogens, not as much as oxygen. So maybe 3.0 for the fluorine or bromine, but that's basically what it's going to show. It's just actually, I'm not being active. But now we got 2 different oxygen here, this one and that one. So these 2 hydrogens are going to appear in the same positions. Well, first of all, the alpha to the oxygen, this hydrogen next to the oxygen, that one typically happens around 3.5, right? I think that's a 3.5. It can happen like it can move 3.5, 3.6, or 7. But after not only having the oxygen pulling it out, it also have a carbonyl. I know this is not on that side, this is actually this side, but still we got 2 electron withdrawing groups pulling it out. So this proton will lose more electron density. So it's going to go more down from 3.5. This will typically happen around like a 3.7, 3.8, maybe it can probably go to 4.1. Because this has a one electron withdrawing group directly on it, but you also have a carbonyl, so it's pulling out more. So that's the reason kind of using these things you need to use to sort it out. The number is wrong. As I said, the most D-shielded one, the most downfield one is number 1. So I should put this one number 1, right? And then that goes number 2. And number 3 is the same. And that's number 4, and this number 5. Sorry about the wrong one. But you get the answer key must be right. I keep reading the wrong. So that is something that you need to do to sort out the real. And this one is ranked by just splitting in the proton NMR, not the carbon. So proton NMR. And then the more splitting 5, less splitting is 1. So on this molecule, which hydrogen is going to be the most splitted? That means which hydrogen has the most number of adjacent hydrogen. That is what it's asking. And then I hope you find out this one, because this one having a not 1 methyl, 2 methyl groups. So that's isopropyl. You got 6 adjacent hydrogen, so this is going to be the second 7 peaks. So along this one, the most going to be the making split one is this one, not that one, because of either end, this will be split only by that. That will be split only by this, but the middle of the chain is going to be split by both of them. So this one having 3 here, 2 there, so n plus 1 will makes it 6 big. So it's excellent. So things like that. What would be the most split one? That would be this one. That has just that side, but there's no hydrogen there, so only this side. So these three hydrogen on that carbon will make it quartet. And then on that one, this one doesn't have no adjacent hydrogen, so that should be singlet. And that one is the same as an isopropyl group right here, so it's the same. You have to say that there's a 3 hydrogen here, 3 hydrogen there, there's a 2 hydrogen here. So you're actually going to have a lot of hydrogens. So this was a singlet because of no adjacent hydrogens. But that was supported by the SH3 on the adjacent carbon. And this one, 3 hydrogen on this side, 2 hydrogen there. So 5 plus 1 is 6. These hydrogens going to split from the sextet. And then this one, 2 methyl groups, 6 hydrogen makes a septet. But that one, 6 hydrogen from the 2 methyl groups and 2 hydrogen from the methylene there, that will make it 8 hydrogen. So 8 plus 1 becomes 9. I don't know how that. Know that? I don't know. So that will be making 9 gigs. So based on that, this question is basically which hydrogen has the most number of adjacent hydrogens. That's kind of the things what it's asking. The next one is this is a proton decoupled carbon-13 NMR. What is a proton decoupled means? The proton on the hydrogen on the carbon, make the carbon be shifted by the number of the hydrogen, but we are disallowing it. So that's why what is called proton decoupled. What it means is each carbon just one page. We simplify the spectrum by doing these things. And what the question is asking, how many carbon signals you will see from each of these molecules, right? But you got to be careful with the symmetry. So for that one, how many different carbon do you see? You got to figure out the symmetry first. Symmetry line goes here, it also goes there. What it means is this carbon is the same as that carbon. This carbon is the same as this one. So just the one carbon you're going to see? No, this one has a 2, right? This one. And then that one inside double bond. So, but this double bond, this carbon double bond, same as this carbon double bond. So we got 2 different carbons. So we only going to see the 2 peaks in the carbon we're putting them on. That one, how many different carbons in the molecule? There's no symmetry there. No symmetry here, no symmetry there. So every carbon becomes different. So there will be 5 different carbons. You are supposed to 5 peaks here. What about this one? This will make all the carbon different too. 1, 2, 3, 4. We're going to say 4 peaks. Well, something that you're going to know is a single bond rotates. That makes these 2 carbons the same. So it's going to be 1, 2, 3 peaks. What about that one? It's going to be the same as a 1, 2, 3 carbons. The trick is double bond doesn't rotate. So this carbon is different from the other carbon. That's what geometry isomerism is. So this one actually has 4 carbons there. What about this one? It's a symmetrical this way, symmetrical that way. This is not the carbon, only carbons there. So this carbon is the same as the other one, just the one half the carbon. So we're going to look at the molecule, figure it out how many different types of carbon in this. And that's kind of proportional. That's the exact number of the peak. You're going to see the proton decoupled carbon 13 NMR. And so if you rank that, what is it? These numbers are 1, most numbers are 5. So I guess that's the number. 5, 4, 3, 2, 1. Yeah. It's a little bit the lengthy question here, because what it is you are doing the reaction using this as a starting material, and then you get product A, B, C, D with the 4 different types of reactions. So your job is trying to find out what are the products and what are the reagents used to create those products. And obviously, this is not everything. There is a IR spectra provided, and using this, and then the other information, the first page, you have to figure out what happens. So several things, I believe you can pick it out easily from an IR spectra. The spectra A have a normal, but we do see these sharp bands at 2200, right? That is the one thing very characteristic. I believe that could be definitely the nitrile, the CN triple bonds. It could be somewhat similar to the carbon triple bonds, but it is somewhat different. We'll talk about that a little later. And then the spectra B, this is a carbonyl right here. But one thing that really giving it out as an aldehyde is these two band at 2700 is really characteristic of an aldehyde. So if you can pick it out, then obviously with the carbonyl frequency as well, but that is definitely the aldehyde. And then C is the one that the triple bond with a hydrogen at the end. And you have a very similar, the band, short bands at 100, 2200, and numbers that can move around a little bit. So you cannot use a frequency exactly. But what I think makes it is a carbon triple bond is not only this signal, you also have that. That is a carbon hydrogen stretching signal. And in CN, triple bonds don't have a hydrogen. So because of that, you have nothing there. But if it's a carbon triple bond with a hydrogen at the end, then you have a bolt. So that's the reason I think this is an alkyne based on cyclamen and the structure there. And then the spectrum B is basically nothing characteristic there. So nothing I can say. So anyway, that's something we can get it out of from the spectra. But you also have other informations, the mass, and also the N+2 mass. And these basically, we're trying to get an idea of an isotope. Typically, the halogen, like the bromines and chlorine. If it's a chlorine, you got an N+2, like a 1/3 of the height of the M. If it's a bromine, equal height of the M. So that's kind of what we can get out of it from this information. And then this number of signals in carbon-13 NMR is telling us how many groups of the carbons in the structures. So I believe that's all we have. But with an IRs and this information, our job is to figure out what is the reactions and then what are the reagents. So the first thing is, this is a isobutanol right here. And then if you just look at this isobutyl part, and then that mass is a 57. If you just add the number of the hydrogen, number of the carbon, you'll get a 57. And then how many groups of the carbons in the structures? You can easily see that it's just 3. Because these methyl groups and that methyl groups are equal, identical. So you've got 1 group, 2, and 3 groups of the carbon. So if nothing happened, then you're just going to see the same 3 groups of the carbon in the carbon spectrums. But if you look at the A here, what is you have an increase of the number of the carbon, right? It became 4. We started with 3, but it became 4. So definitely something happened. We probably added a carbon. And then we already know from the NIR spectra, it is a nitrile. But in case you didn't even see the NIR spectrum, you can resolve it. This portions of the structure is 57. The mass is 83. So if you subtract 83 from the 57 from the 83, you have a 26 left. So we need to figure out what could be the 26. But 26 is just 1 carbon and 1 nitrogen. Carbon 12, and then nitrogen is a 14. So CN makes a 26. So that is also giving it out. We have our nitrile added to these isobutyl groups. So this is kind of what we're going to do. From that information, we say this will be our final molecule. of the spectrum A. And then in order to make it happen, you have to substitute hydroxyl groups with the nitrile, but of course, the CN, you cannot directly attack the hydroxyl groups and kick the OHs out because OH is a really bad leaving group. It won't go. So in order to make the OH goes, you have to either make it part of the good leaving groups. That's what this tosyl chloride does. When you react in the alcohol with the tosyl chloride, now the oxygen becomes a part of the leaving group. So when you react in the nucleophile, like a cyanide, it attacks this, as I said, two reactions and kick the tosylate out, so you get the substitutions. So that is basically reagents are required to make the products. We only care about the final molecule of the spectrum A is a nitrile. It doesn't need to be tosylate. You could either do the halogenation reaction, right? You can react with the thionyl chloride or the PCl3. That will make an acid, alkyl chloride, or PBl3, they make an alkyl bromide, and the nucleophile makes an attack. Would the same thing. So you can choose different reagents in the first step. But second step is gonna be the cyanide, right? Because then we gotta use it as a nucleophile. So that is A. And for the B, what is a characteristic here? First of all, the number of the different carbons, 3. It's the same number of different carbons. So I don't think we added any carbon here. Mass is a 72. And then we start from the 74. So what happened was that we had a decrease in mass, but just 2. 2 could be just 2 hydrogens. So we actually take out the hydrogen molecule out of starting materials, and that is definitely oxidations. I mean, from the IL spectrum, we already know it's an aldehyde, but even without it, we know that the mass decreased by 2, so it must be the oxidations. We start with an alcohol, you oxidize it, you've got to have an aldehyde. But obviously, your IR spectrum is actually supporting these organisms, showing that those characteristics 27, 2800. So oxidation from the primary alcohol to the aldehyde, then you can use a variety of oxidant, PCC, PBC, chlorines, strong oxidations, but not the chromic acid, not the dichromate, because if you're using such a strong chromic acid reagents, then you get the carboxylic acid. And you still have to choose wisely for the oxidant. And then C, now the mass can increase again, 82. That's the one that is acetylene in the structures. If you remember that carbon triple bond with the hydrogen at the end. So let's say if we can still work it out without that. Mass got increased, and then 0% M plus 2 isotope means there's no halogens here. Number of the signal got in carbon increased to 5 from the 3. So clearly we can expect that 2 carbons got added. If you subtract the 57, these isobutyl portions with an A2, we got the 25. And 25, you have to have a little bit of an experience to figure it out, but that could be, if you have a 2 carbon, that's a 24, and then still have a 1, that could be hydrogen. So this is easily pointing out that. With a smaller number of mass, there's only a few possible combinations. We can figure it out even without an IR. But we gave it an IR because we don't want you to keep guessing what it could be. But that is definitely makes sense. Acetylene moieties, 2 carbon with 1 hydrogen is oddly makes a 25 mass. And you're not seeing 25 mass that easily in other ways. So that is definitely confirming that we got acetylene groups, and that 2 carbon added makes sense because we got number of the carbon signals increased from the 3 to 5. So that is kind of confirming, all the way that we have acetylene structures in the products. This has been produced from that, so it's kind of the same thing. We have to make our hydroxyl groups, lipid groups. So tosylations or the halogenation. And then with the nucleophile, with the acetylene ion, different nuclear bond. This is a chapter 8 stuff, if you remember that. If a triple bond, you can take the hydrogens out of triple bond by using sodium amide. That makes it nuclear bond, so you can make a reaction with a primary alkyl halide phosphate. So it's kind of very similar manner. You prepare that, you're reacting with acetylene moieties, and then you make this tosylated D, and then you get the substitutions. So that's pretty similar. This N+2 didn't really do anything for the first three, but for the B, we got the about 32% N+2 sig height. So that is a kind of a pointing out that we have chlorine. Right? So we got chlorine in the structures. But what is odd is we start from the 3 different carbons in the isobutyl groups, but we got 2. So you may think that this may be the structure, just substituting the OH with the chlorine, but if that's the what is, then you should have a 3 different carbons still in the product, but we got 2. So it cannot be simply this. Chlorination happened, but somehow the molecule becomes more symmetrical. That's the reason why it's only showing 2 peaks in the carbon 13 NMR. So that is kind of pointing out that this is not simply just substitution of the OH with the chlorine. So what is happening is we think it's still the isobutyl group, because if you take the chlorines out, the molecular atomic weight of chlorine is 35. So if you take the 35 out of the 92, you still get the 57. So that's the same mass of the isobutyl groups. So it's not like we cut the carbons out. We got all the carbons, all the 4 carbons in the structures. Yet, molecule and the product becomes more symmetrical. That's why it only gave 2 signals in the carbon 13 NMR. And then how you can explain 4 carbon making just 2 signals is a kind of, you have to imagine that it becomes like a T-butyl. That way, the 4 carbons can be grouped as 2 carbon, 1 and 2 carbons with 3 methyls identical. So how that happens from that? It cannot be done by simple substitution. The carbon skeleton changes typically involve the carbocation formations. So what you need to do, you're gonna treat like a strong acid, like HCl, then you're gonna make a water leaf. It's gonna make a primary carbocation, which is not stable. One thing that I've been keep emphasizing to you is, as soon as you're using the carbocation, you gotta start concerning about the rearrangement, because that's the really characteristics of the carbocation. Carbon ion doesn't rearrange that easy. Radical doesn't rearrange this easy. I mean, of course, they may rearrange time to time by different type of mechanisms. The carbocation rearrangement is really common. So that's the reason I think this reaction has to go through the carbocation to allow this shift happens. Especially this is primary alcohol. So if you make the water leaves, then you got the primary carbocation, which is not stable. So molecule is going to look for any possible way to become stable, which makes a rearrangement. So one of these, basically a hydrogen shift there, then you got the tertiary butyl carbocation. You keep in the tertiary carbocation very stable. The chloride capture the carbocation, and you can have a PBD. So this is kind of what you need to do to solve this problem. And then, of course, in the test 1B, this is a question that students spend the most of the time to get everything right. But you can see that you have to prepare yourself to solve a mystery question like this in the test. There are other questions here too. From the A, B, C, D, I put the structures here because we moved on. Which ones are most oxidized? You remember that the chart that I gave you to consider, carbon being oxidized or reduced. If you give a molecule oxygen, that's oxidation. At the same time, oxidation can be done by taking the hydrogens away. But if you're adding hydrogen with oxygen, like adding water, that is not an oxidation, that is not a reduction. You got to consider like adding halogen or the nitrogen is also kind of oxidation too, same level of oxidations. So those things are something we need to consider. So for instance, I want to say that the alcohol and then the alkyl halide, these are kind of the same level of oxidation. I mean, of course, the more reduced versions such as hydrocarbon, carbon will just the hydrogen. If you add oxygen or the halogen, we are going to say that the carbon is going to be oxidized the same level. At the same time, you also should consider that making a double bonds is also oxidation too. So these are basically the same levels of oxidation. There's a one more level of oxidation done by making like alcohol to the like carbonyl. You take the hydrogens away, that is an oxidation. But at the same time, we already talked about taking the hydrogens away is an oxidation, like making triple bonds. That is also oxidation. So these molecule, any of these molecule, we consider is more oxidized compared to any of the molecule down there. I mean, from this to that is an obvious because you take the hydrogens away. But if you need to compare the oxidative state of this and that, may not be that easy because one is a triple bond, one is an oxygen. So you got to really counting in how many oxygens there, how many hydrogens be removed away. So sometimes it's not that obvious. So that's why I'm giving you these examples to pointing out that which ones are more oxidized, which is less oxidized. But this is not the top of the line. There's one more level of the oxidation, which is basically adding oxygen to this, it will be the carboxylic acid. But substituting this carbon with the nitrogen, that will be another oxidation. If you think about that, nitrile is more oxidized than just the triple bonds. So if you can figure that out, what will be the most oxidized out of the four? That would be this, right? That one. So that would be A. And then you should choose the same oxidative state, then the triple bond with an aldehyde, those two. So that would be B and C. So B and C are equally oxidized. So once you know how to do the adding oxygen, taking hydrogens, and the combination of that with nitrogen, halogens, and this isn't too hard once you know what to do. All right. The next question 3 is a mass. You will definitely get a mass spec questions. It may be like this or maybe different. But this one is basically asking what are the structural fragments you see. And this is a molecule. We got molecular weight is 148. You got the 148. So that's basically this molecular ion. But don't put this structure down here. I mean, of course, that's what it is. But what you see in the mass has to be the positively charged, right? The molecular ion is the radical cation. So we were looking for this in the structure, not just entire structures, but you're going to specify what you see is actually molecular ion is a radical cation. Of course, these radicals, which bond is the radical, we don't know. That's why we just put the radicals for the entire structure. That's why we use a bracket. But that's a simple one. This is a ketone. So what would be the probability that it's a base peak? Is a more stable fragment can come out of this would be the resonance stabilized one, right? So what makes a resonance stabilized fragment? I mean, of course, you can break down the structure based on breaking any carbon bonds, but especially I want you to think about alpha cleavages. If it's an alcohol, amine, something that's a carbonyl, alpha cleavages is definitely one of the fragmentation to use a resonance stabilized one. So it's based alpha cleavages of cleaving the bond around the carbonyl. It could be this bond, it could be that one. But let's say you cleave this bond, then you're breaking up, having carbonyl positively charged. That's something called a psyllium ion, which is a resonance stabilized carbocation. And then that yellow part is going to come out as just radical, the propane radical. So you gotta make sure that, what's the mass of that helium ion. So, this is basically the resonance structure of the helium ion. Oxygen has a lone pair. So when they see the carbocation and next carbon, lone pairs can come in, make a triple bond. So it makes a resonance structures. So that's the reason why the alpha cleavage grows very frequently, because it makes a stabilized carbocation. But anyway, the propyl parts of 43, you take off the 43 from the 148, that's the 103. So we are supposed to find out the structure of the 103, and that is basically the structure of the fragment by the alpha cleavages. So that, but this is not the radical cations anymore. Remember that? We break down the radical and the cation. So this is just the cations only, not the radical cation. Then we need to find out. This is the 103. That's the biggest peak there. The base peak is corresponding to this one. 120. We need to find out what appears 120. Well, there are many things happen, but if you remember, the ketones, the carbonyl with the gamma hydrogen. There's a hydrogen at the gamma position. This is the Y next carbon, the alpha position, beta position, and gamma position. If you have a hydrogen at the gamma positions, what happens is it goes through the special rearrangement called the McLafferty rearrangement. So that is something that you have to keep in mind. It is not happening for every molecule, but it happens with a molecule with its gamma hydrogens. So this one has it. So what happened was this electron goes to get the hydrogen, that electron goes to the carbon, make a double bonds, and then this bond breaks and comes here. You break right there between the alpha and beta carbons. That's the bond they broken. So you got a double bond comes out, and this becomes like a ketone, is evo forms. So this is the molecular 28 comes out. So we got 120 is definitely the fragmentation done by the McLafferty rearrangement. This, we remove the neutral molecules out. So McLafferty rearrangement, still the radical cation. That may go through the further fragmentations, just like when you take out the water in the alcohol, that still go for another fragmentations. But that's the basically with 120 signal. That's kind of small. I mean, radical McLafferty rearrangement is not the most stable the fragments. So you may not have this base peak, but it happens. So these are kind of the things what we expect, and this is what it shows in the spectrum here. But the next question is, if you change the structures to this, then what will happen to each peak? If you remember that 120 peak, that's coming from the McLafferty rearrangement, right? In order to have a McLafferty happen, you have to have a gamma hydrogen. This molecule don't have a gamma hydrogen. The chain goes to alpha position and the beta positions, and that's it. No gamma hydrogens. So what that means is McLafferty cannot happen. So 120 peak will disappear. But what about 105 peak? If you remember what is 105 peak, that's the alpha cleavages, basically breaking down from there. So let's see what happens if you break down this bond. Same way, you make that helium ion, and then you are having a propyl comes out, but the radicals on the two positions. That's what it is. The previous one, you break down from that same position, but it makes a primary radical. So these are helium ions equal. We have to think about that stability the same. But the radical stability are different. This is a secondary radical, this is a primary radical. So it gets more stabilized, it will happen better. If you change the structures to this, to that, 105 peak should go up because it becomes more stable, it will most likely happen more, even though that was a base peak already, but it can even be even more higher. So something like this, you should think about structure will change the spectrum, and then you should relate to that. And then this was basically another different molecule and finding out what is the most intense fragment. As I said, this is the carbonyl right here. There's many things can happen, but alpha cleavage is something that you can expect. But alpha cleavage can happen either breaking this bond or breaking the other bond. If you break this one, you get that silicium ion to this side, this ethyl as a radical goes out. If you break that one, you make a direct silicium ion, then you got the radical next to benzene, which is a benzylic radical. Okay? You've been seeing many times, benzylic radical, these radicals stabilize benzene. This is way more stable than the other one. So which one will be the most intense fragment you will see? That one, right? Because of it, the stability of H ion, this and that is almost equal, but the radical side, that's way more stable than the other one. The combination of both, this one is more stable. So that's the reason that one I think will happen to be basically. So something like this. I don't know what else I should think about the mass spec. Well, the mass spec side, if it's really structural determination, you got to solve the structures. We don't normally solve the structure just by the mass spec, but you could eventually do it. We're looking at the fragmentations, right? And then finding out what comes off. It's going to be very tedious, calculations of what fragments are made, how they break down for the overall structures. And that is kind of what you need to be able to prepare. But know the most stable fragmentations, right? What that means is a stabilized one will happen more. Alpha clip is definitely a means to make those more stable fragments if they have an oxygen organ or the carbonyl. But if they don't have those things, then the molecule will break down based on the structure. Still, we can break it apart proton bond, but the more substituted, highly substituted carbocation will be the most stable ones, and we can look for that. Backgravity is kind of special one. Alcohol backings are somewhat difficult because dehydration can happen when alcohol, under that high temperature to the highly energetic state by electron being knocked out, the OH goes out as a water. So you get the dehydration peak shows up. But alcohol also make alpha cleavages. Alpha cleavages are probably what that you should use to get structural information, what's around the OH. So that should be something that you should use to kind of put the pieces together. Amine does that too, right? Alcohol does that, amine does that, those carbonyl containing ones, So alpha cleavage is a part of something that you really should be able to handle well. Magnetic is special cases, I said. But the halogen, sometimes you can get a clue like what we did before. The N+2 isotopes can give you that you have a chloride or the bromide. Those possibilities can narrow down the structures. I don't know what else I should talk about in the mass spec. So yeah, that's probably most of it. It sounds easy that actually doing it, but that's what you should do. But moving on, the NMR side, is now there's a lot more things going on. These questions are pretty simple. It's asking how many different series of proton NMRs. So we got to count up, how many different type of hydrogens are there. So these hydrogens at the carbon A is actually same as the hydrogen and carbon F. So we have one group of hydrogen from that methyl group, two different methyl groups there. And then the second one is the one inside, but this was the same as the other one. And then third one is the one from here. And in carbonyl don't have a hydrogen, so we can skip that. But this benzene, they got this hydrogen is equal to that one, but not with this one because the difference is substituted on those sides. So we got fifth groups of hydrogens are on that side. No hydrogen there, no hydrogen here. There's a hydrogen there in methyl groups. There's a 6 groups of hydrogens. And that one, we got 2 hydrogens. Are they equal? Is these hydrogens equal as the other one? I think that's the one many people made a mistake on that time. This hydrogen on that side is different from hydrogen from this side. This is a cis to the benzene, that's a trans to benzene. Double bonds make these two different. If this is a single bond, then this one's and that one's illegal. So you got 7 different groups of hydrogen there. So I think that one was a probably a lot of people made a mistake that time. How many different carbons in the same thing? We just kind of count up. This one's the same as that one. This one is the same as this one. That was the difference. So we got 3 different groups of carbons here. Now the carbon of the carbonyl, we should count. That doesn't have a hydrogen, so it doesn't show the signal of the proton anymore, but the carbon proton anymore will see the carbon of the carbonyl. So that's a fourth one. And then there's a 5th one, if the benzene is carbon without the hydrogen, we should count in. So that one we should count in there. This carbon same as this one, that one's the same as that one. This one is different from that one because it's not symmetrical this way. This carbon, different that carbon, and this carbon. So all together, there will be 11 carbons. I think people made a mistake of not counting in these carbonyl carbons, or some of these carbons are at the edge of the benzene. They just forget that, proton, yeah, sure, they don't have a proton, so you don't worry about that, the proton anymore. But the carbon 13 anymore is based on the carbon. You gotta count the carbons, even though we didn't worry about that, the proton anymore. But, multiplicity questions, this is kind of finding out how many neighboring hydrogens there. This carbon, the hydrogens on carbon A, it has a 3 hydrogen here, but that's not what it's split by. It's split by the hydrogen in an adjacent carbon. It's a CH2, the 2 hydrogen will split this hydrogen triplet, right? N+1 rule, for 2 + 1 becomes 3. The B, having 2 groups of adjacent hydrogen, there's 3 hydrogen here. There is a 1 hydrogen there. So we got 4 total adjacent hydrogens plus 1 makes 5. So it's going to be quintet. Carbon C has a 2 hydrogen here, but it also have another carbon group. So even though these 2 are identical, but that means that this hydrogen and that hydrogen, we're going to add together. So 2 from here, 2 from there, and then base plus 1, that will be also another quintet. So we got that split to 5 pigs. And that's also the one that people made an error. That's hydrogen here. And so this one looks like that's definitely this one and that was the difference. So these should couple to each other. But people also consider that one to split that one. The thing is that these hydrogens are too far away. Remember that if that's not the carbon, if that's the hydrogen, this hydrogen will split this one. But this is on carbon, so these are 1, 2, 3, 4 ones away. Hydrogens on the 4 ones away, they don't split. So that's why these methyl groups don't do anything for that hydrogens. Just these 2 will split each other. So that's why it becomes doublet. This will be doublet by that will be doublet by this. And then this CH3 on the carbon O, that basically standalone hydrogen, that will be just singlet having no adjacent hydrogens. So when we do that, just be careful. The 2 hydrogens are 4 ones away, they don't split. Even though it looks close, but so you may just thought that they're going to split each other. No, it's gotta be within 3 bond members to make the splitting happen. So I'm pretty sure that this is type of question that we could use to like a ranking question, rank the molecule based on the how many pigs the hydrogens or particular hydrogen can be split to. You can have questions like this and things like that. Okay, which carbon? Carbon. So which hydrogen will be the most downfield shift in the proton angle? That's a simple one, right? If you're looking at the chemical shift table, the carboxylic acid will be definitely offset, and then aldehyde, then aromatic ones there are two different aromatic hydrogen here, 1 and 2, like hydrogen H, hydrogen I. But which one is going to be more initiated? That's something you also need to figure out. Then I should say that hydrogen H is better because that will be more initiated because this side you go close to the carbonyl electron withdrawing groups. The other side we got double bonds. So this is not electron withdrawing groups. So these electron withdrawing groups, that's like donating groups. So hydrogen close to electron withdrawing groups will lose molecular density. So that's why it's either H or L, not I or K. I mean, we cannot figure out which one because it's symmetrical, but at least H is better than I or K because it's closer to the electron withdrawing groups. And then which one's going to be most upfield? That's definitely the most saturated carbon without any electron withdrawing groups. I would say the furthest away, the single chain is based with the A or M. The same as by the symmetry. And then the carbon 13 NMR, the most the downfield shift, that's a carbonyl. The carbonyl carbons is showing over 180 regions. So that's definitely the most downfield shift of the carbon 13 NMR. So you gotta, these questions are pretty simple ones, but you need to remember the things that is we discussed in the class. Yeah.
For E, why isn't C an option? It's only an
This one, why C is not an option? C is this electron withdrawing groups. C is closer to the name, right? As I said, when you get next to it, you get electron pulled out the most. This is the furthest away, so that impact of electron withdrawing groups diminishes as it goes further away. So this is the furthest away from the carbonyl. That's the only electron withdrawing groups there, except the anisotropy, which is done by the shape of the molecule. So that's why we're talking about the most upfield one. This was the furthest away from the electron withdrawing groups. So C's are too close. That's my answer. You should be expecting reaction question because of chapter 10 and 11 is oxidation of an alcohol and reactions of alcohol. We got the chrome trioxide and sulfuric acid. That's basically the strongest oxidation that you could do with alcohol. They will convert primary alcohol to the carboxylic acid, right? Secondary alcohol to ketone. So this is the primary alcohol. That will becomes the carboxylic acid. But the many people are confused about this one. So you can keep going backward. This one. That's an alcohol. They try to oxidize this one too, because they see this as a reagent. Their mindset was, I can oxidize any oxygen there, basically. This becomes a carbonyl, that becomes a carbonyl. They just keep thinking that I gotta change that. But if you make a carbonyl of this oxygen at that carbon, that will make a bind on the carbon. So tertiary alcohol don't get oxidized because you cannot make a carbonyl out of it. That was kind of a little bit tricky with this question. A lot of people miss that one. Primary alcohol, yes, it will become an aldehyde. Then aldehyde get oxidized further to the carboxylic acid. Secondary alcohol, it just becomes a carbonyl. But hydroxyl groups and tertiary carbon, it will not get oxidized because there's no way you're going to make a bind with the carbon with the carbonyl there. So that was the kind of the things we kept time. The second one is a very popular question for the test one. You see here, we got alcohol here in the stereochemistry. And then we have a reagent given as PB of V. You have to understand that phosphorus, bromide, tribromide will substitute OH with the bromine, but it will do it with the inversion of the stereochemistry. So we are looking for that answer. You should invert the stereochemistry of the bromide in the structures. But don't invert this one because nothing happened to this bond, right? So this stays same. Only that one is going to be inverted. Brominations are, PBr3 is the only reagent right now we teach you, so it always comes with inversion. But if it's a bromination, then you have choices, right? The PCl3 will invert the stereochemistry just like this one does. But if you're using thionyl chloride, SOCl2, then it won't invert the stereochemistry. It will keep it same. So that you got to be careful about those two reagents for the bromination. Depending on what you need to do it, you got to choose the right one. Inversion stereochemistry, you got to choose a PCl3. With the retention of stereochemistry, you got to choose a thionyl chloride. The next one, the proiodic acid with a diol. Proiodic acid alone is not the thing. You're gonna have a diol. You're gonna break that carbon-carbon bonds, and then you're gonna cap each end as an aldehyde or ketone, depending on their substituted level. It's a singly substituted carbon, so it will become an aldehyde. If it happens to be doubly substituted, then it just becomes a ketone. But proiodic acid will break the carbon bonds of the diol, then either cap it as an aldehyde or the ketone, depending on the substitute. So that's what it is. And the reagents are kind of what you should remember for what it does. This one, you got strong acid. HBr is no doubt is a strong acid. It will protonate alcohol to the water. Then water may come up that will leave a carbocation right there. And then the bromide will capture the carbocation, and you get to make bromination there. So most of people actually wrote that down as an answer, and then we were happily pointed out that's not right. Why that is not the right one? Because a hydride on the adjacent carbon can shift, and it will make a more stable tertiary carbocation. As I said, anytime you see carbocation, you got to worry about the rearrangement. That is something that you just have to keep remembering until the end of organic chemistry. So this is kind of a trap. We lay out the trap so you actually fall down to that. And then a lot of people did. And they explained this to you so you don't do that again. Anyway, so you understand why this is not the answer. It happened, but this carbocation rearranges, makes a more stable carbocation. That captures the bromide. So you get that as a product, not this one. If you answer that, you get a partial credit. That's just get the full credit. All right, this one, you got alcohol, you got acid chloride. What happened was this alcohol makes an attack to the carbonyl. So this makes an attack to the carbonyl, make these tetrahedral intermediates, but this has a leaving groups of chlorine. So what happened was that these electron pairs of an oxygen comes back, remaking carbonyl by kicking the chlorides out. So that's a common mechanism of this acid chloride or that carboxylic acid derivative. So you can make an ester, but again, that's pay attention to the stereochemistry. It's not the inversion because you see here, nothing happened to these carbon-oxygen bonds. It stay the same, and that should stay the same. But don't just try to invert or to retain for no reason. You gotta look at the mechanism and try to see what will happen. But you see that this oxygen may attack that one, but nothing happened to this carbon, so these stereochemistries should be the same. The next one's pretty simple if you know what sodium hydride does. Sodium hydride is a just strong base. That's what you can say. The base is needed to take the protons off of the alcohol. Sodium hydroxide is not good enough for this hydrogen because sodium hydroxide is going to be a good base, but this proton on alcohol is less acidic than that. So sodium hydroxide, unfortunately, cannot take the protons off of the alcohol. Only alcohol that loses the hydrogen to sodium hydroxide is a phenol. Phenol is a benzene with an OH, that's a phenol. If you take the hydrogen of the OH with on benzene, it will make a resonance structure. That's why the hydroxyl groups on benzene becomes acidic. Then sodium hydroxide will be able to take it off. Then you can have an epoxide like this one. But if it's a regular hydrocarbon, then you're gonna use a strong base like a sodium hydride or sodium metal. Extreme cases, you can use sodium amide. But that first step is just a deprotonation step. You get the nucleophile, you have alkyl halide. So this is just nothing but a central reactions. So you get ether formations, and this particular reaction is called the Williamson ether synthesis. You make a nucleophilic oxygen anion from an alcohol and do the SN2 reactions that to make a ether. So that's what it is. So I mean, there's only a few reactions in chapter 11, so I don't think it's going to be too complicated. The next ones, of course, PCC. You got to know what PCC means. This, the chrome trioxide mixed with the HCl and then period. It makes a mild oxidant. It will oxidize secondary alcohol to ketone. That's the same. But on the primary alcohol side, it will oxidize just to the aldehyde, not the carboxylic acid. So we are looking for that. But sometimes people forget that PCC or PDC, cholines or whatever, they oxidize secondary alcohol to the ketone too. Sometimes they just focus on this one, they make that one, leave that one saying it's an OH, and that is not right either. It oxidizes secondary alcohol too. It just doesn't make any differences between the most stronger chromic acids versus PCC for secondary alcohol, but they also oxidize secondary alcohol to the ketones. Anyway, so these are the reaction-related questions. They're only limited to the number of reactions that we talked about, so I don't think it's going to be too much big deal. The next one is going to be a series of the reactions and the questions on the spectroscopy questions. What the questions asking, finding out the structures that gives out the spectra. So this will take significant time, we give a molecular formula, so whenever you see it, you should calculate the degree. I think that will sometimes help. So degree saturation, number of the carbon, you subtract the half of the hydrogen, you subtract the half of the halogen, you add a half of the nitrogen, and plus one. Don't forget a plus one at the end of the formula. So if you do that, that will just make a one. So we got 1 degree of unsaturation. So that could be double bond, that could be cyclic structures. We don't know what it is. So from the IR, what we should gather from the IR is we have a very strong band there. That should be very noticeable. And then I know this, the trick that the scan quality is bad. So let me give a number. This is about 1650. So if you see the carbonyl band, 1650 region, that means that you have an amide. Carbonyl having a nitrogen. So that's fine. But the thing is that these regions, the 3300 region, we see two spikes. I mean, these signals are pretty big. So you may think that this may be coming from the oxygen or maybe the alcohol. So that's why I've been telling you this intensity of the signal of the OA to NH is kind of relative, but you cannot say that NH is always small. This is an NH2. You got two spikes because of this 200 there, but this is pretty big. You see this go all the way down. So mostly the NH signals are smaller than OH signal, but they're always an exception. This one's a particularly, put it this way. So, but don't get fooled by the intensity of the signal. This is a 2A NH bond. I'm saying that because two spike is not easy to see. If it's an OH, it's probably just one giant band put it together. You're not going to see two spike. So anyway, so this amide, primary amide, that's what we call, makes out this one and that one. Other than that, there's not much we can gather from the spectrum. One thing for the NMR, now we know this 200 on nitrogen is suggested by this two spike of the IR. These 200 is very broad band. That I think is an NH2. The hydrogen on oxygens, hydrogen and nitrogens are more broader in the NMRs. This is kind of way more broader, but that is basically what this NH2 making very intense the hydrogen bonding. So that two hydrogen broadband broad peak of the NH2 peaks NMR is kind of a saying that this was that one. But what else we should think about? This is 6 hydrogen becomes a doublet. 1 hydrogen, I know you cannot make how many peaks that's good too, like that looks like, I don't know, many, but 1, 2, 3, 4, 5, 6, 7 probably. That these combination is something that you're gonna find out. These are isopropyl groups. But anyway, you should get into the habit of taking off something that we know, so you kind of figure out what we should deal with. These entire molecular formula by the NIR, we figured out you have to have a amide bond. So 1 carbon, 2 hydrogen, 1 nitrogen, 1 oxygen. If you subtract that out, it's just 3 carbons and 7 hydrogens. So if you figure out what it is, then that's everything. So we don't have to look for any other pieces. So from that, these 6 hydrogen should be the 2 methyl group. There's no way 1 carbon can have a 6 hydrogen. It gotta be 2 carbon with 3 hydrogen each. So 2 methyl groups has to be identical. And then next to the 1 hydrogen, that's why it becomes a doublet. This one's typically the pattern of the isopropyl groups. So if you recognize the isopropyl pattern, then you have an easy time to solve the structures. This is isopropyl groups. And then you only have this piece and that piece. So you just have to put it together, and that is the structure of this molecule. So this one's a pretty simple one. The next one, let's see. Next one's not too difficult, but you still have to think a little more. We got 6 carbon, 11 hydrogen, 1 bromine, 2 oxygens. Again, degree of saturation, it's giving us like a 1. So we got 1 degree of saturations. And then that 1 degree of saturation could be related to carbonyl. That one is close like a 1740. So that means that we have an ester, right? These 2 oxygens is probably oxygens of the ester. So we can get that from here. And then on the proton NMR side, we got 9 protons, singlet. If you see a 9 hydrogen comes on singlet, there's really not many occasion. That must be P-butyl groups. I know this is kind of experience is telling, but you should solve enough problem to understand what it is. 3 methyl groups become same equal methyl groups. It's not easy. It's very special for the P-butyl groups. So this means that you got the P-butyl here. And then the neighboring carbon, you got no hydrogen, that's why it becomes singular. So that's basically what it makes sense. But you got 2 hydrogen here, also becomes singular, but not only that, it appears between 3 and 4. That's the critical information. So how it becomes a critical, let me show you. Is that 2 hydrogen, these 2 means the number of hydrogen here. So 2 hydrogen is a CH2. I don't know what it is, it must be CH2. It should have electron withdrawing groups. Otherwise, it wouldn't come this far. So it has electron withdrawing groups, but carbonyl is not going to be long enough. Because if you have a carbonyl, it could be like a 2.2 reason. If you have a 1 oxygen next to it, then it'll pull down maybe almost somewhere around here. So that could potentially mean we have an oxygen in the 1 corner. That's a possibility. So if that's the one, then we got 2 pieces. We still have to get the bromine put somewhere. So how are we going to put it together? We got P-butyl part, and then we got, so 6 carbons, so 1 carbon, 2, 3, 4, 5, 6. We found all the carbon pieces there. We only need to put it together. So it's putting together, it could be this way. We got P-butyl that comes this way. You got ester here, BCH2 comes, and then bromine here. Will this be the structure that making the spectrum? So that is something that you're gonna have. For finding pieces is something that you're gonna do first. But connecting the pieces together, you have to think about, are there other ways to put the pieces together? For instance, P-butyl maybe go to this side, not that side. next to the oxygens, and then the carbonyl, and then the CH2 comes and the bromine goes here. So how can we figure out which one is the right answer between these two structures? No matter what, I think T-butyl is going to be still far away from the grease in the electron withdrawing groups, not in a beta position. It's going to be probably over here. Only thing that we can figure out between these two is a chemical shift of this. So this CH2 signal peak comes between 3 and 4, right? Comes between 3 and 4. Having just one oxygen will make this hydrogen goes that far. But these structures has another bromine here. We got two electron withdrawing groups directly bound to it. So this will pull, that will pull. So if that's the structures, this proton here is going to go somewhere between 4 and 5. It's going to come really far out. So somewhere this region, I think very close to 5. That's what it's going to show. So that's the reason I don't think these are structures. Now, on the other hand, carbonyl, we'll pull it out to like a 2.2. And then it also have a bromine that further shifting out. So it's, with the carbonyl, it will be just by here. But bromine will shift it further. It just landed on the where I'm expecting it. So having these CH2 appear in these regions, I think it must be that structures. This will be too more shielded from that. So you gotta use that chemical shift to figure and double check what is the right choices in case you are having a multiple options. So this is something that I want to explain. And the next one from the IR. This one is pretty high. If you see that it's 1500, 16, 17, it's almost like 1800. By the degree of saturation, is still 1. And then it's 1800 carbonyl. The carbonyl 1800 is not common. Most of the carbonyls are 1710, plus minus like a 30 or 40. But going out to 1800 is not that common. But there are a few occasions you get that high frequency carbonyl is like an acid chloride, carbonyl having a chlorine bond to it, or it becomes a very constrained, the cyclic structure, carbonyl within the constrained cyclic structure. But having a chlorine in the molecular formula is kind of suggesting that we may have an acid chloride, or we don't know. We just have to keep in mind. But carbonyl is already 1 degree saturation, so I don't think it's going to be cyclic carbonyl. If that's happening, then the degree saturation should be more than 2. So I think it's acid chloride, but let's not consider it at this moment. We just have to pay attention to these are way high the frequencies for the carbonyl. And then what else we should think about? Yeah, there's a the 6 hydrogen doublet and 1 hydrogen manipid. I mean, this is kind of a saying we've been talking about isopropyl groups, right? Isopropyl groups here. But this is CH2 doublet. This CH2 having 1 hydrogen in adjacent carbon. So I think it's got to be right here. That way, this 1 hydrogen will make this one doublet, make these 2 methyls doublet. So actually, this one may not be 7 pig. It could be probably how many pigs has to be 6 here, and there will be 2 here, 8. It should be 9 pig from here, but obviously. We cannot make how many pigs it becomes, but it'll be really, a lot of pigs down there for the 1 proton. That's what makes it very small. But anyway, having a doublet for this CH2, only way to have a CH2 doublet is having CH next to it. So that's why I put the CH2 right here. And let's say what else we need to find out. So it's 5 carbon, 1, 2, 3, 4, 5. So we found all the carbons, and I believe we found all the hydrogen. 9 hydrogen, this is 6, 7, 8, 9 hydrogen, 1 oxygen from here, we're missing 1 fluorine. So we just have to put it together. So if you put it together that way, that will be just acid chloride. The only thing we're missing was a chlorine groups here. That chlorine has to go to the carbonyl because that's the only open spot. So then putting this to that will be the structures. So these ones are, in a way, not too difficult as long as you know that you accept the fact that this acid chloride carbonyl becomes pretty high, the wave numbers. Even though you didn't know about it, still, that's the only way it makes sense by putting things together. The next one is pretty small molecule, 3 carbon, just a 3 carbon. And then IR, you have a somewhat broadband. This is 3,000. Sorry for the bad scan quality. This is 3,000. So we got the broadband with the 3,000 centered, and then that means that that's a carboxylic acid. And then if you potentially expect a carboxylic acid, you gotta have an NMR showing really high chemical shear, like over 10 offset proton. We call that offset peak. Over 10, you see the 1 proton there. That also makes sense to the carboxylic acid. That is something that we should find out. So we got 3 carbons, and then if you see this, I mean, again, this is a quartet, it's triplet, and then 2 hydrogen for the quartet, 3 hydrogen for the triplet. This is basically the pattern for the ethyl groups, CH2, CH3. I think that's all the carbon that we need to find out. These ones are just put all together there, and then the answer, right? That's the only thing that we can think of. So this is a pretty simple question. The next one, it has a lot more complex proton anymore, so it may be a little difficult. It has a 5 carbon, 10 hydrogen, 1 oxygen. So equivalent saturation, if you do that, still 1. But we don't see any carbonyl. So there's no, not the carboxylic acid, no aldehyde, no ketone, nothing, right? No CO double bonds. But we do have an OH, right? Because these bands, strong band, over like a 3,000, 3,300, that must be OH. So we have OH groups here. That makes sense with the oxygens. And then I don't know which peak is going to be the oxygen, the hydroxyl peak signal there, but it got to be there. This one, I mean, it looks like that could be the OH one, but we'll see. But one thing that you have to see that this 5 and 6 region, they got so many peaks right now. That's a double bond region. All together, 3 hydrogen, so many peaks. I mean, number of peaks, there's a 4 peaks here. Actually, these are 2 peaks, 2 peaks, 2 peaks, 2 peaks. So these actually have a lot of peaks there. This one, if you see that, that is a vinyl. That's the vinyl groups. If you don't know what the vinyl group looks like, that's what it is. So you can probably make out. And that double bond is basically what makes out this one equivalent saturation. So we got vinyl groups, and the vinyl groups have about 2 hydrogens and 3 hydrogens altogether, 3 hydrogens. And these ones, I'm sorry, that one's us. Yeah, this one. Yeah, these ones are probably this split the most. The trans and then cis, this one makes that one. These 2 will make those 2 because it's fine splitting between the 2 of the hydrogen, the same carbon. Splitting constant, very small. So anyway, the vinyl makes out this type of pattern here. So that's a vinyl. And then you see here, there's a kind of many things, 2 hydrogens, 3 hydrogens. What I should point out that is, these hydrogen here is between 3 and 4. So hydrogen can come down this far, should have an oxygen boundary. If there's no oxygen here, this hydrogen cannot come this far. So having a pretty issue with hydrogen there, that means this hydrogen and the carbon should have an oxygen here. I mean, we already know hydroxyl groups there. So that I put the hydroxyl group right here because of the chemical shift, this proton is still pretty high. And then it's a quartet. So what that means is this one is a several hydrogen next to it. Anyway, this is 1 hydrogen we have to think about. And then between these 2, we can think about them. Maybe CH3, this maybe CH2. It's kind of a little more than the quartet. Looks like it's a quintet. 1, 2, 3, 4, 5. But anyway, so this triplet means that this is a triplet having the 200 next to it. So this must be that one. This could be this one. And then this one has to come down there because that way, this one hydrogen and then these 300, these are splitting this one into the 5 peaks. So this kind of makes sense why this becomes a more than a proton. And then this is kind of the only one has to go there because we will have a 5 part 1, 2, 3, 4, 5. There's no other pieces there. So this has to go right here. That they got the final structure. So and then OH signal. That's the only only one that we can assign. So that must be the one that hydrogen and oxygens, and they become a singular too. So almost time. I don't. Yeah, the last one. I think it's the last one. Let's go quick. I don't know how quickly we're going to go. All right. We got peaks right here, right? That means that we got triple bond. It's a CN or CC triple bond. I don't know what it is. It's a but the thing is, if it's a terminal alkyl, the acetylene, we should have a CH stretching here, but we don't see that. So that means it's not the acetylene groups. It must be the nitrogens, CN triple bond. And then that makes sense for the 2 degree saturation is coming from the CN. That's 2 degree saturation right there. All right, on the proton and negative side, we got the methyl groups with the singlet. What that means is that we should have something like oxygen next to it. That's why we pull down this bar, 3 point like bi regions. And the 2, CH2, triplet. That's another thing I want to recognize. This becomes a triplet means that they're right next to each other. That way, this H2 makes that one triplet, that H2 makes this one triplet. So that makes sense. But this was a more shielded. The one of these groups has to be next to an oxygens. That way, you got this one pulled out this far, that one comes here. And then on that side, we should have something else there. That will be the only piece left, which is the nitro. The nitro is electron withdrawing groups. So that's why these ones are more deshielded than that one, because the 2 electron withdrawing groups is next to that one. So once you find out the structures, you have to make out the reason why each one showing a particular NMR. So that would be the way you can actually double check your answers. And believe me, if you don't double check, you are bound to make a mistake. I really hope that you do. It depends. Well, that's all I'm going to say today.